Everybody, welcome back. My name is Umut Acar or Acar, whatever you would like to call it, it's fine. And I'm accessible at that email or my first name at cmu.edu. Okay, good. So I'd like to start by getting a pulse of the room a little bit and trying to understand that the backgrounds that we have here, so that we can kind of bring everybody on the same page as much as we can. So I'd like to start with the following question. I've recently had a little accident, so I'm limping a little bit, but hopefully I'll feel better in a few days. So question is, how many of you think that the answer to this question is positive? How many of you think that parallelism is hard? Raise your hands. Okay, let me count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Well, it's going to be easier to count. How many of you think it's easier? Okay, how many of you think it's easier? Okay, 1, 2 people, 3 people. Okay, parallelism is easy. Okay, you guys, you lost. 3, and minus 3. This is pretty clear who the winner is, asymptotically hard. So for those of you who think it's hard, what's hard about it? Yeah?
In parallel and implementing it, so basically designing an algorithm with parallelism in mind.
Good. Thinking in parallel, i.e. design a good parallel algorithm. That's excellent. Excellent, excellent, excellent. Indeed, this can be hard, eh? Okay. What else?
Honestly, the associated counting problems are stressful. Like, if that...
Explain that, please. Yeah.
Like, when you're figuring out what an algorithm does and when you're analyzing an algorithm,
Okay, I think what you're getting at is, so this is like a little bit about efficiency, right? I think what you're saying is correctness is also a problem. Like you look at the algorithm and how do you know that thing does what it's supposed to do? Am I getting it right?
That's also a thing that stresses me out when I read.
Okay. I think we should add parallelism, thinking parallel design, good parallel efficiency. Efficiency is an issue. It can be stressful to think about what the algorithm does. Yeah. Yep.
I was going to say, especially correctness in the face of shared data.
Correctness in the face. Awesome. Correctness. Okay. Well, this is pretty much the life of a computer scientist anyway, right? So are there anything else I'm missing here? How much to do in parallel? Okay, how parallel should I go? I think I would put it into this maybe efficiency bucket, right? Maybe, you can say, I can come up with an algorithm that's parallel, but it's not, incredibly parallel. Maybe that's okay, right? So how do you assess that the efficiency that you got is good enough, okay? Okay, so basically it comes down to these two things. Yeah, I'm missing something. Go ahead, yes.
Also getting the speed up on actual hardware, which comes
down. Good. So that's excellent. So let's split this into theory and practice, right? Okay, good. Okay. Right. So what we hope to achieve in these next 4 or 5 days is to change this, to flip this. Hopefully, we'll take a vote at the end of the 5th day, and then hopefully these two numbers will swap. That's the goal. If we can do that, okay, we've accomplished our goal. Otherwise, we'll have to try again. Okay, so we'll take it the same poll again. So really, our goal is to convince you that parallelism is really not that hard. And it's actually not that much more difficult than sequential programming. In fact, if you guys think of the days where you've learned about sequential algorithms when you were undergraduates, it was tough, right? Remember that algorithms course where you had to design efficient algorithms? It was tough. I mean, that's not easy stuff, okay? It turns out that I can perhaps, we can perhaps like take, if it was possible for us to go back and teach you that course, including parallelism, you would have thought it's hard, but you would not have thought it's harder than what you've achieved, what you took, actually, right? So I think what I'm trying to say is that we can teach you parallelism, parallel algorithms, just about as in the same difficulty as your classic sequential parallel algorithm. We've done this on, right now, thousands of students with thousands of students. Thousands of students have learned to design parallel algorithms, implement them, and so on, right? Both in theory and practice, up to a point in practice, primarily in theory. So this is possible, and we'll try to get the ideas across as to how this is possible. Now, one of the key ideas was the idea of language-based cost models. Okay, so why is this important? This is important because it raises the level of abstraction for us. Okay, we are human beings. We are miserable beings. Okay, we can barely keep in mind 7, 8 things in our heads. Life is miserable, right? Like, I mean, you ask me what I ate 3 days ago? Oh, good luck. I have no idea. Okay, 7, 8 things. Okay, this is miserable. And this explains, I mean, I think this is very important. I feel like I have great empathy and sympathy in life to a lot of people. And I feel that this explains the state of the world in many ways, okay? The world is a complex place, and human beings, we kind of like muddle about it, just like trying to understand. But we were miserable things. We can barely keep in mind 7, 8 things, okay? We need help. And language-based cost models give us that without deceiving us. Okay, that's very important. So they give us a way to reason about complex objects, complex mathematical objects, in a faithful way, in a way that does not deceive us, does not mislead us. It's very important. So they are abstract, right? They're abstract, they're high level, but they're also truthful. What we mean by this is that they reflect the actual cost of things reasonably accurately. Okay, so as an analogy, I'd like to, as a way to explain this, I'd like to use an analogy. Suppose that you go to a restaurant, and then you tell the server, with your friend, you tell the server, okay, this is what we would like to have, okay, and then the server tells you. And then you ask how much would that cost? And the server tells you, well, let me go check. It's going to depend on a lot of things. You're like, what do you mean it's going to depend on a lot of things? Well, he comes back and tells you, well, today our boss boy is out of, called in sick, so we hired somebody else. He's a little bit more expensive. Our chef, like our chef de cuisine is sick today. We hired another guy. He's working overtime, so he's more expensive. Cucumbers today are more expensive than what they always used to be. So your price is going to depend on all of these things. You're better off to first eat, and then we'll tell you what the price is. How many of you would accept such a thing? None of you. Okay, good. I like that. Okay, that's a little bit like what machine models are, right? So you kind of have to run the thing first, either in your mind, or you have to go down to that level of, okay, is this register ready? Can I put this in here? Is this processor ready? Blah blah. Is this chef ready? How much does cucumbers cost today? And then you get a cost. I mean, this is not for us miserable human beings, right? This is just way too much complex. So what we would like is cost models that allow us to reason about things, programs, algorithms at the level in which we write, which is the programming language, right? So when you go to the restaurant, you look at the menu, you know what you're getting, and you know what the cost is, you're done, okay? That cost is both abstract and it's truthful, because presumably the restaurant is making some money out of that, everybody's earning their lives, so It's both truthful and it's abstract, so it achieves that. So all we're saying is that we want computer science to be as advanced as restaurant business, okay? It's a lot to ask, it turns out. Okay, anyway, so any questions so far? Good, so moving on, I'd like to point out a key assumption that we're going to make throughout that is going to allow us to flip this vote, okay? And that is, we are assuming pure functional programs. If we don't, what happens is that parallel programming becomes incredibly difficult because of shared data. Your friend raised the point that if you've got shared state, okay, and if you've got multiple actors, be it processors, be it threads, be it whatever, reading and writing that shared state, the semantics becomes incredibly difficult. Again, for us miserable human beings who can barely reason about 8 things, the semantics becomes incredibly difficult because you have to now reason about exponentially many interleavings of code. You know, imagine 2 pieces of code, these 2 agents, each of them are executing a 10-line algorithm. How many different interleavings do I have to worry about? Any ideas? If I want to, let's say that they're just adding, there's a number here and they're like checking the number, making some conditionals and checking things like if it's 1, make it 2, if it's 2, make it 3. Some piece of code like that, each one of them is running 10 lines of code. How many different interleavings would I have to reason about to think about the correctness, to prove the correctness of this algorithm? 10 factorial, what are 10 to the 10, is that, what was that one? Or 10 squared is another?
10.
What about 2 to the 10? Good. It's good. I like diversity. Diversity is good. So, right, so we basically have to worry about, let's figure this out, we have to worry about, we have 20 lines, right? When they both complete, there are going to be 20 instructions that are executed. And for each one of them, how many choices do I have? Basically 2 choices. It's gonna, because these are sequentially executing, so it's gonna either come from that one or from this one. So let's call this guy A, let's call this guy B. You know, I've got A, B, you know, A, etc. Right? So there are 2 to the 20, okay, different interleavings that we have to worry about. So now in a typical system, you'll have, right, in a typical parallel system, you don't have just 2 agents. You typically have, let's say, okay, let's be very, very modest, and let's say you've got 10 actors. You've got usually much more, but let's say that you've got 10 actors, okay? And a typical algorithm will probably have like 100 lines of code because the lines of code is assembly language, okay? So that's basically the number that you're looking at, okay? How big is that number? Does any of you have any ideas? Yeah, this is huge. It turns out that this is number greater than the number of atoms in the universe, known universe. Okay, for us who can barely think about 8 things, this is a big number. So basically, it becomes impossible to reason about the correctness of algorithms when you allow shared state. That's a very simple demonstration of why what the challenge is. Yeah. How many people write? That's a good question. I have no idea. So the question is, how many people write parallel programs? I have some idea. It depends on what you count. Pure. It's a very complex question. It depends on what you count. Pure. It depends on, like, our algorithms. Our students all write pure parallel function programs, I can tell you that. And we've so far educated thousands of them. you can say MapReduce is a purely parallel computing, a purely functional model, if you cross your fingers a little bit, right? So yeah, so I think that question is I'm not sure how to answer that. Yeah.
You're suggesting that pure functional escapes the shared state problem.
Good. So the point is that, right? So so this illustrates what happens if you've got shared state. Basically, you can't even reason about the correctness of basic programs. When you've got purely functional programs, all of this goes away. This problem doesn't exist. You know, we are back to our usual selves. The 7, 8 things that we know that we can keep in our minds, whatever, is sufficient to reason about purely functional parallelograms. It's perfectly fine. Okay, it turns out. Because this problem simply just doesn't arise. There is no such thing as shared state, mutable state in a purely functional program, period. Okay? It goes away. Now, it's very important that this is also an abstraction. Now, you can say that, what can I do at all without doing updates? Okay? Indeed, you're right. You can't do much without doing updates. But it is an abstraction in the sense that as a programmer, you don't have to think about that, but the runtime system can use that. Okay? It's the fact that you can't use it doesn't mean that the runtime system can't use it. The runtime system can't use shared state, do all kinds of mumbo jumbo. As long as it's proven correct, as long as it does the right thing, you're fine. Okay? So this is an abstraction that's offered to you as a programmer so that you don't have to worry about this, okay, problem. Any questions? And we'll see examples of this, what we mean by that. We'll give you, we'll present you data structures that are purely functional, behave purely functionally, but implemented using updates under the hood. Okay, good. So this is an important assumption, which is why Guy talked about lambda calculus, right? That means that lambda calculus ends up being an excellent model to actually both write parallel programs and also reason about their cost. So once we make that assumption, then Guy mentioned, so once we have the purely functional programs, Guy then presented a cost semantics, right? And this cost semantics is just, you know, it's simple. It's got just a little twist on what you're used to. Okay, what's that twist? What's the little twist? Anybody can explain to me what the twist is? Yeah?
You're counting the number of steps in your evaluation dynamics.
You do that anyway in sequential programming.
Okay.
So what's the twist? Sorry? It's inherently parallel. That's good. Okay, that's good. That's nice. Let's keep that in mind. So good. So one, inherently parallel. What he means by that is that in the way that Guy explained it, if you have an expression, if you have an application like this, you can evaluate this thing and that thing in parallel.
It's called by value.
It's called by value, right? So we can sometimes we write this just to make sure that this is perfectly clear. In fact, it also makes it easier, right? Sometimes we write this, but you can omit that. What we mean by this is that these two expressions can be evaluated in parallel. And every time you see an application, you can evaluate them in parallel. You don't have to think about anything because there's no such thing as shared state. That's very important, okay? But what's the little twist when it comes to cost? So in a sequential programming model, what do you think about in terms of cost? What's the thing that you care about? Yeah? Just work, okay? You only care about work, which is the same thing as saying sequential runtime. Because you can only do one thing at a time, the work amounts to total sequential runtime. So in a parallel model that Guy introduced, what do we have in addition to that? Span, okay? So this is the twist, okay? So in a traditional algorithms course, you only think about that. And then you say, okay, I do this first, it's going to cost me 1 unit of time. I do that next, it's going to come in, blah, 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 right? That's how you reason about things. Now here you have span, okay? So this is additive, right? Work adds up. Little twist in span is what? How do you calculate span? Max. Excellent, right? So the difference is, instead of being additive, you take the max. So this is why, this is not too hard. Because, well, as you learn about that, as you're used to reasoning about the work of your algorithms, it's not that hard to also reason about the span of your algorithms. I mean, you just have to figure out, okay, these two things can be done in parallel, I have to wait for them to terminate, and then, I go on, right? It's very simple when it's done at this level of abstraction. Okay, any questions? Okay, so let's do an example. Okay, just to see, just to etch this stuff in our heads a little bit. Just do a little example. Okay, so I'm going to just write some ML code. Okay, so this function takes x, and it says, if x is less or equal to 1, then return x, else, or, is x, or else, we want to do something like this. So I'm going to use explicit parallelism. Okay, so I'm going to say AB is f of x minus 1, comma, f of x minus 2, and then turn this into parallel. Okay, so all I did was basically recursively called my function on x minus 1 and x minus 2. Okay, and I simply return a plus b. Okay, so that's my function. Yeah?
So the two pipes is like a comma but parallel?
Exactly. 2 pipes is a comma but parallel. Okay, good. So one way to reason, we can now calculate the work of this, right? What do? We say, given some value n, we check if n is less or equal to 1, it's that. So let's do that. So work of n is 1 if n is less or equal to 1. Otherwise, work of n minus 1 plus work of n minus 2 plus, for that 1, okay, otherwise. Is that clear how I wrote that? Yeah.
Do you mind writing a little bit bigger?
Yeah, definitely. Good. So this is, thank you, work of n minus 1 plus work of n minus 2 plus 1 otherwise. Okay? Any questions about that recurrence? Very simple, right? Good. So that's that. And now I can, now I'm going to need to think about span, right? Let's write the span. Span follows the same model. Well, it's 1 if n is less or equal to 1. Otherwise, what do I have? Okay, I'm going to run these two things in parallel. Max of those, good. Max of, this and this, okay, plus 1, okay? And that plus 1 is because of that. So let's, now to just dive a little deeper into it, so what we can do is we can say, okay, this function evaluates as follows. Take some n, and then you get some other recursive stuff here, okay? So let's actually give an example. Let's say that n is 3. So I'm going to get n is 2 here, and n is 1 here. Okay, so the 2 is going to fork off into 1 and 0, and that's going to terminate. Okay, that's just going to return. And then it's important not to understand that here this double pipe means that we have to wait for both of them to complete. So we're going to have what's known as a join node here, a synchronization. All the edges go rightwards here, right? So we're going to have a join, and then plus A plus B. We can put A plus B into that join node. And then here, this is again going to return, and then we're going to have a DAG like this. And the span corresponds to the longest path in this DAG from the source to the sink. And work corresponds to the number of vertices, assuming that we create a vertex for each unit piece of work. Any questions? Okay, why is this a DAG? What's a DAG? Directed acyclic route. Why is it a DAG? Can it have cycles? No, we don't. We can't have cycles. Otherwise, we won't. Good. That's why it's a DAG. Can I have a funny DAG like this? Would that be a reasonable DAG? That looks like a reasonable DAG, right? That's a DAG. There are no cycles. But what you will notice is that this is sometimes called nested parallelism or fork join parallelism. You won't have a DAG like that. Well, let me make it a little more complicated. Like, you might have a DAG like that, but for example, that is a DAG, but that won't be a proper DAG that represents a fork join program. There is no fork join program or nested parallel program that corresponds to that DAG. So basically, we'll generally be working with a subset of DAGs that have specific invariants. And what's that invariant? The invariant is that once a part of the DAG is spun off, there is no more communication between that part and the other part. Okay, so you can't have edges that cross across parallel boundaries. So that thing and that thing don't communicate, synchronize, in other words. That is very important. They synchronize only at the end. Okay? But you will see, for example, BJ might talk about that this afternoon and later. There are many different flavors of parallelism. So you can have fork join, which is what we have here. You can have async finish, which is slightly more, slightly richer. You can have futures. In futures, you can have dependencies. You can have synchronization edges like this. You can have DAGs like this. So many different flavors. Here, we're going to focus on fork join parallelism, so we're not going to see DAGs like that. But basically, everything that we talk about here will generalize to futures. I don't know of anything that specifically will not generalize. But be mindful that there are different paradigms or different primitives for expressing parallelism. Questions? Yeah?
Why is it maximum work for the DAG?
Oh, excellent. Sorry, that's a typo. That's proof of my 7 brain cells. Okay. Questions? Yeah.
So is there some easily tested property of graphs that tells you if it's
Oh yeah, definitely. The question is there a property of graphs that tell you that they are the right stuff for fork join parallelism? Yeah, these are called, for better or for worse, series parallel DAGs. And the idea is that they're built recursively by either composing them sequentially or by composing them in parallel and adding a join node. It's just the usual constructive definition. So series parallel DAGs are DAGs that are formed by sequentially composing in this fashion or by composing them like this. So they have to be disjoint, obviously, between. Okay, good. So that's it. So you have work and span, and that's all you have to worry about. So your cost model is, if you can say 2x more complicated than the original cost model, 2x is within reason for our lifetimes and for our evolution. I think we seem to be able to handle that kind of complication, right? I bet you can learn to design good algorithms that have low span. Okay, what's a good parallel algorithm? A good parallel algorithm, we want the work to be as close as possible, right? So what's a good parallel algorithm? It has to be, this is called work efficiency, in the sense that it has to be basically, you'd like it to be no less efficient than the sequential algorithm for the same problem, and you want it to be low span. And typically, low span means log D, and any log, polylog span is fine, asymptotically speaking, because logarithm function is, the point is that log is such a slow-growing function that your work is generally going to be at least linear, n over log square, n over log cube, n over log 4. This is going to create plenty of parallelism because you care about parallelism at large problem sizes, right? So parallelism is important when the problem size is large, and when the problem size is large, n is going to dominate log, so no problem, okay? Questions? Okay, excellent. So this is the abstract part of the cost model. This is, recall that I talked about two things. One of them was that the cost model needs to be high level, right? So it's a high level cost model. It's very simple to reason about. It's good. Now the other part was that it needs to be truthful, meaning that I can tell you I define span as 0 for all algorithms. That's not truthful, right? We need to be able to, that's a little bit like, okay, no jokes. So we can't do that, so it needs to be truthful. How do we make it truthful? What we do is we basically design a concurrent algorithm, right, that pushes the complexity into the runtime system that realizes that cost model by offering a provably efficient implementation. Okay, so let me write that down. So what we do is we realize the cost model by designing algorithms that realize the model on actual hardware. So these are called, different names for them. You can say provably efficient implementations. Another term that you'll see is bounded implementations. Okay? So basically, what you want to be able to do is this. Somebody comes up with an algorithm, and then they give you the work in span. Okay, so that's what they give you. And then you want to give them a programming language in which they can implement the algorithm with the given work in span and reason about the work in span in this fashion. And you want to guarantee certain things about the execution. What do we want to guarantee? Okay, let's think about that a little bit. Suppose that you want to run any given algorithm on a machine that looks like this. So it's got some memory, okay, and it's got some cores. Maybe like, we have 6 cores. And these guys are connected to the memory with some kind of bus, okay? So we want to run such an algorithm on a machine like that, what we would like our guarantees to be. Any ideas? Excellent. Oh, I like that. Okay, the results should be the same. Excellent. That's very important, right? We want to be able to say that we want the programmer to be able to reason about the algorithm as if it's a sequential algorithm, and when we execute it in parallel, they ought to get the same result. Okay? That's sequential semantics. This is why we work with lambda calculus, right? Because instead of those pipes, the parallel ones, you just execute it sequentially, you get some result, and it's provably the same if you execute things in parallel. So this is sometimes we call that we say that parallel algorithms accept sequential semantics. Okay, so you can reason about your algorithm as if it's a sequential program. You don't have to run things in parallel. This reduces the burden on the programmer incredibly. It's just basically a sequential program for the purpose of correctness. Okay, so that's excellent. We want that. What else do we want? Okay, good. We would like the parallel algorithm and the sequential. This algorithm should be, that's more of the property of the algorithm, right? I think what you're saying is that the algorithm should perform just about the same amount of work as the best sequential algorithm. That's more like the property of the algorithm. That's an excellent point. Let's suppose that this is a work efficient algorithm. Still, like, what else do we want to be able to offer to the programmer? Something more, maybe? Yeah. Good, excellent. Translation between the costs. So when I run this algorithm, right, on my machine, what I could do is I could say, yeah, I have this incredible language, man. You can give me your algorithm. I'm going to guarantee that it has the sequential semantics. Okay? Well, because I run everything on a single core. Okay, obviously. We don't want to do that, right? So we want to be able to take advantage of all the cores that we have as much as possible. So that means that we want to exploit the parallelism that the algorithm has given us. Okay, what can we do? Let's think about it. How much more efficient can we be in terms of runtime? Let's say that we want to bound p-processor execution time. Okay. Any ideas? It's going to have to be W over 6 or W over P, right? On this machine it will be W over 6, excellent. It's going to have to be at least W over P. We can't do any more than that. Okay, anything else? Plus span. We certainly know that as well, right? It can't be more than span because we have to respect the dependencies. Right, so I can't, in my function here, I can't execute this in my example before I execute that. I can execute that before these edges must be respected. Therefore, the runtime cannot be less than span. Okay, so these are lower bounds. Can we give an upper bound? Okay, Guy suggested an upper bound, right? And it turns out we can, but let me first tell you that it turns out that many different versions of this problem is actually NP hard or complete. Figuring out the optimal execution time for a given DAG with some given specified work and span is an actually NP complete problem. Many different versions are NP complete. But yeah.
Opt, what does it say?
That means that an algorithm that figures out that comes up with the optimal execution schedule, meaning the shortest time, is NP complete. Okay, but of course, as with many NP complete problems, this doesn't mean that we cannot approximate it. Okay, so it turns out it's very easy to approximate in theory. So now I'm going to show you the algorithm to do that. Okay. Now suppose let's go back here. Let's try the first thing that we can imagine. How can we execute such a schedule on P cores? Sorry. How can we execute such a DAG on P cores? Any ideas? What's the first thing that comes to mind? So let's say that I have, 1, 2. Let's say that I have just 2 cores, and I want to execute this such a thing. I start, at node A, right? Let's say that processor 1 at time step 1 executes node A. Okay, as soon as I execute node A, B and C come alive, right? Because now they can be executed. So I can assign them to 1 and 2. Okay, that's time step 2. And then when B and C execute, then I have D, E, and F. Oh, not F. No, just D, E. Okay? Those two. So I can execute the NE. Okay, and then I have F and then G to execute, right? For F and 5G. Okay. Right, so this is called a schedule in the sense that it maps the vertices here to time steps and processors respecting the dependencies. Okay. Now the algorithm that I used here, even though it probably wasn't apparent, was a level by level schedule. It starts at level 0. When level 0 is done, everything at level 1 can be executed because all of their ancestors are executed, so we can execute these two. When these two are done, everything at level 2 can be executed. Those are those guys. Level here means the longest distance from the source, right? So these two guys can be executed, and then level 4, 5, and so on. Any questions?
This is called Brandt scheduling.
Breadth first scheduling? Very close, but a little bit different. In breadth first scheduling, I would execute G before all of these guys are executed, because it will be actually, as soon as I execute that, that would be available for execution. So that's why the terminology can sound funny. Level by level is intentionally trying to say that it's not breadth first because of this problem. So G, that's a very good question, right? So the question is, isn't this breadth first? It's not. Right? It's very important to notice that it's not. Because in breadth first, you could go to G as soon as you're done with C. Yeah.
But what about depth first scheduling? In depth first, we go to the entire tree, right?
Yeah, so if you did depth first, you'd also run into trouble, right? Because you could go to A, C, and G. Oops, but then this is not done yet, right? So what's very important is that a vertex must be executed after all of its ancestors are. Whereas in breadth first and depth first traversals, you can go visit a vertex as soon as you can, right? If you can reach it, you can visit it. That's what makes scheduling difficult, is that you have to make sure that all the constraints are that's why it's NP complete primarily. The reason is that you have to make sure that all of its dependencies must be completed before it can be executed. Okay, questions? These are very good questions. Very important, subtle, very important differences. Any questions? Okay, good. Now, okay, so it turns out this level by level scheduling, we can give it an upper bound on that one. Let's do it, okay? So what I'm going to do is I'm going to define W sub I as the total number of vertices at level I, okay? Then by definition, W is I from 0 to, well, let's count from 1. What's that? The sum of I from 1 to span Wi, okay? That's trivial, right? Now, so my level by level schedule is going to proceed as follows. I finish W0, W1, W2, W3, one by one, waiting in between. So my total runtime is each level takes this much time, right? Because I can execute everything in each level in P chunks at a time. If you've got a million things at level 10, I take P of them, run them, I take the second P chunk, run them, and so on. Okay, so that's how much time each level takes. And I have my sum, okay, from 1 to S. Right? Very simple arithmetic. Now, this, let's rewrite this. This is I from 1 to S, Wi over P, plus 1, right? That's just, again, simple arithmetic. Now, let's take the 1 out, right? So we get I from 1 to S, W over P, plus S, okay? So I pull the S out. Okay, now what's this term? Okay, so that's less or equal to, again, like some simple math, W over P plus S, because that was floor, right? What's that term? That's just W over P. Total big W over P plus S. Okay? So this level by level scheduling, very simple, gives us WP over P plus S. This is what Brandt proved in 1974. It's called Brandt's theorem. It's ancient. Huh? And it's the main, right? So it's important to reflect on this. It's very simple, but it's very powerful. Because here we have an NP-complete problem. And we are able to approximate it within a factor of 2. I claim that this bound is no more than 2 times opt. Why is that? Okay? So this is no more than 2 times. It's a factor to the approximation. Recall our 2 lower bounds. What were they? Good. So one of them was this, and the other one was this, right? This means that TP is greater or equal to max of WV of that. Okay? So that means that opt is greater or equal to max of WV. And you have it. Okay? Obviously, right? So because it's correct. Okay? So it's a factor to the approximation. We're good. So here we have a theorem, very, very simple theorem that says you can solve this problem you can approximate it, very well by using a very simple algorithm. Now that is something that's worth to build a cost model on, right? It's basically saying, look, man, your chef may not appear that day. That processor may be busy, okay? Your cucumbers might be expensive because, suddenly some processors that are working on making the cucumbers is expensive. But we can still give you, okay, we can still guarantee that the cost of making that meal for you is going to be W over plus S, no matter what happens in the world. And that is very important. And then we can say, okay, then this proves that at least theoretically, you can be truthful to that cost model. So if the algorithm has is work efficient and it has low span, it's got the best of both worlds. That means that its runtime will be on any number of processors not too far away from the best possible thing. Questions? Okay, yeah.
Opt over here, you basically just mean this T is super opt.
Yeah, it's the same. Yeah, it's the same thing. Yeah.
Well, the cost of that.
Yeah, the length of that schedule. Yeah, the length of the optimal schedule. Yeah. Okay, questions? Yeah, you have something? No? Okay, good. Okay, good. So now this is a little bit of a wasteful algorithm, right? Because why is it wasteful? Any ideas? Yeah.
I'm sorry. What's the difference between length of a scheduler and its own cost semantics? Essentially, is there a work? Does a scheduler have a work in depth? Because you said this, a scheduler is an algorithm.
A scheduler is an algorithm, yes.
Right? So we're only interested in its length, which is a different measure than its cost or its depth.
This is a very, very good question. Bravo. I was trying to sneak it by you. You have more than 8 brain cells. So, I didn't mean that literally like that, sorry. Yeah, so it's an excellent, excellent question, right? So the cost of the scheduler versus the length of schedule is very important. So the length of schedule is the TP that we've been talking about here, right? TP is the length of the schedule, 1, 2, 3, 4. This particular schedule has length 5. Now the scheduler that computes that schedule, we did not account for that so far. We did not account for the cost of that. We basically just constructed a schedule, and then we bounded its length by W over P plus S. Okay? Now, we did not reason about the cost of the scheduler. Yeah?
So you mean length of schedule and cost of scheduler?
Right. Right. What I mean is that
Here you have cost of schedule and length of scheduler.
the length. This is the cost of the scheduler. Sorry. And the length of the schedule. Yeah, sorry. Yeah. Terrible handwriting. Sorry about that. So the length of schedule, this is the TP that we are interested in. We are interested in minimizing T sub P. Now, what we did not talk about is the cost of the scheduler. And I think this is an excellent question. I'd like to just hold off for a second. Just notice that this is an issue. It's a very important point, okay? But let's go back and then go back to our original thing and think about the length of schedule a little bit. My question is, so this particular scheduling principle, or like this scheduling scheduler that I suggested is the level by level scheduler that says, I'm going to execute first everything in this level. When that's done, I'm going to execute the next level. When that's done, I'm going to execute the next level, and so on. Okay? That's a bit wasteful. Why? It waits a little bit. Can you see when? It waits a little bit unnecessarily. Yeah.
Well, you can't do F and G now.
No, yeah. This example doesn't demonstrate, unfortunately, but yeah, think about it. Yeah.
It forces you to always be at the same level in technical computation, whereas you might have available processors that you can use for something that's deeper down.
Exactly. I think exactly. So this let me demonstrate that. Suppose that you've got, excellent point. You've got like many jobs here, but the number of jobs you have is, I don't know, 10 times P plus 1. Okay. So you go through these things in P chunks at a time in 10 steps. At the 11th step, you're executing that one little guy, and all of your other 5 processors, however many processors you have, P minus 1 processors are waiting. They could have proceeded to the next level, right? And that is not going to harm anything, is it? Seems like it shouldn't, right? It's not going to harm anything. Okay, it seems like it shouldn't. Yeah, I mean intuitively, right? Good. So that variant is called greedy scheduling. Okay, so the variant is, or a greedy scheduler, let me just use this, is a scheduler that basically greedily maximizes processor utilization regardless of levels. Okay, so it doesn't care about levels anymore. It says, well, if one of those vertices are available, if I can run it, I'm just going to go and run it. Okay. If exists idle processor and exists ready vertex, assign. That's the greedy scheduler, okay? If there's an idle processor and if there's a vertex, I'm just going to assign it. I don't care what level it is, and etc. Okay, so it turns out this also guarantees the same bound. But we did a little bit of an improvement. Something like that. Okay? Do you want to see the proof? Okay. So let's see if we can wiggle out of the proof with my 8 places in my memory, so we'll try. So it's a very elegant proof. I haven't come up with it or anything like that. I'm just channeling it to you. It's I'm borrowing it from Aurora, Blumhoff, Plaxton, 1997 or 8 or something like that. Okay, it's a classic paper. By the way, this research area, this 1974, is perhaps the first known result. It's been active since then. Even today, it's an incredibly important area, right? There are many, many researchers whose life has gone into studying variants of this problem. So it's pretty cool, sophisticated stuff. So now this result, this proof goes as follows. So what we're going to do is we're going to have a work bucket. Okay, and we're going to have a idle bucket. And we are going to imagine our processor is executing. At each time step, if the processor is busy, it's going to toss a coin into the work bucket. Okay? If it's busy doing work at that step, it's going to toss a coin into the work bucket. If it's idling, it's going to toss a coin into the idle bucket. Okay? So in each step, we collect P coins. They either go to the work bucket or go into the idle bucket. Okay? Therefore, TP, runtime, is exactly total coins divided by P. Why? Because we collect P at a time. So let's keep this on the side. Yeah?
So what exactly is work bucket?
Yeah, so the point here is that if the processor is working, it's going to put its coin into the work bucket. If it's actually idling, it's going to put it into the idle bucket. And the intention here is to keep track of who's doing what. It's just the analysis technique. Okay? Now, in the work bucket, how many coins are we going to have at the end of the execution? W, exactly W. So this is going to be exactly W. Okay? So the only interesting one is the idle one. Okay? That we need to worry about. So let's think about the idle one. So we put, how many coins can we put into an idle bucket in any step? What's the max number of coins that we can put into the P minus 1? Excellent. Why? Because the computation hasn't done yet, right? At most P minus 1, obviously. Very nice. Okay? Now, visualize how this schedule is executing. It's greedy, remember. If there is a ready task, it's going to assign it to processors. Imagine a step at which there was an idle token, there was an idle processor at all. Any step in which there was an idle processor. Now imagine the processor is kind of eating away. You've got some DAG, processors are eating away into the thing. Now imagine a step at which there was an idle processor. Can you say something about the span of the remaining DAG? So if these are the nodes that we've executed, the remaining DAG is this thing. What can we say about the span, the longest path in the remaining DAG? It's minus 1, right? It reduces by 1 because you've executed everything at that level. So therefore, you're making progress on the span. So the key observation here is that every time you have an idle, if at a step you have an idle processor, you must have finished a layer of your DAG. So this can only happen times S times, because there are S layers in your. So therefore, the total number of coins in here is at most P minus 1 times S. Okay? So total number of coins, therefore, is less or equal to W plus P minus 1 times S divided by W, and then you get that bound. Okay. Very elegant, right? That's very nice proof, yeah.
P is essentially like height, right?
No, S is essentially like height.
Well, I mean, previously we had the DAG like left to right with sources.
Okay. Oh, I see what you're saying. Okay, yeah.
You switch it to
Yeah. Oh, okay. Oh, sorry, yeah. Good point, yeah.
So when source is left and sink is right, P is height, right? And DAG.
P is however many processors you have.
Right.
But it could be, it would make sense at most for it to be height, so to say, yes. Yeah. That's sort of the most number of things you can use, yeah. Okay. Excellent. Very good, right? So I think basically, again, like what I've shown you is that a very simple algorithm can give you this bound. And it turns out you can implement these things on multi-core machines and so on, right? Okay, so that would minimize the 10 lines of code to implement this thing, right? But again, coming back to the excellent question your friend asked, what's your name, by the way? Quinn. Excellent question Quinn asked. The point here is that all of this theory does not take into account the cost of actually computing the schedule. The cost of the scheduler is completely unaccounted for in all of this theory, okay? Now, but I mean, it's a trivial algorithm. It's just like saying, is there a processor idling? Yeah. Is there a ready vertex? Yeah. How much can that be? What do you think? Think about this. So, I mean, how complicated can this algorithm be to implement? Is there a big deal, this cost of the scheduler thing? You have doubts. I think you're sensing that I'm a little cheating you. Okay. What could be the complexity? Any ideas? Yeah.
Very centralized. It's very centralized. Someone needs to keep track of all the work.
Oh, awesome, beautiful. Yeah, good, very good. So, what's a natural way to implement this? A natural way to implement such a scheduler is to keep a work, queue, if you wish, and then you've got your processors. The processors go to the work queue, right, take the task. At each step, what happens? It's very centralized. This work queue can only serve one thing at a time. How is it supposed to serve in one step these 4 things? Okay? You need to travel at the speed of light in order to cheat the time-space constraints of physics, right? So, or you need to live in 2 different universes. Okay, so this won't scale. Indeed, if you implement this algorithm in this way, it just won't scale to more than 10, maybe 15 processors. Okay, what can we do? Excellent. Yeah, very good. So we do distributed queues. Okay, instead of centralized, what we do is we use distributed queues. Okay. So now, while I do this, I'm going to generalize the model a bit more as well. So far, I've given you a DAG, right? We don't need to know about the whole DAG. What we're going to instead is imagine a model in which a vertex executes. When it executes, it can spawn new vertices, like in this model. I could start executing this vertex. When it executes, it spawns 2 vertices, okay? And then we have 2 new vertices. And then when that executes, it spawns 2. When they finish, they synchronize here and so on, Okay, so all of this is happening in an online fashion. So what we can do is have these separate queues. Let's say that we put A here. This processor takes A, runs it. When A runs, it's going to create B and C. So then it pushes, let me cross that so that it's persistent. So it's going to push B and C inside its queue. And then next, it's going to take, let's say, C. Okay, it's going to execute C. C is going to, no, that's a bad one. Let's do B. CB. Let's take B. So B executes. It's going to create D and E, and so on, right? So what we can do is locally we can basically manage this as a stack. Okay, I wasn't careful. Let me write it like this: C D E, where the processor pops one, executes it, and then if the execution of that vertex creates new vertices, it pushes them onto its stack. Okay, so it treats it just like a basically regular, at lower level speaking, like a call stack, basically. Okay, so you can imagine it as if this is a call stack. So it's working like that. Now the problem is that with this model, all of these other processors are idling. So we need to somehow find a way of getting these vertices from here to all the other processors, and that's sometimes called load balancing. Okay, this reminds me that I need to do some load balancing and change markers because otherwise they dry out. Good. So we do, we need to do some load balancing. What's a good way to do load balancing? So one way that historically has proven to be very effective is that if there's an idle processor, what it does is, if the processor is idle at a step, it uniformly randomly picks any other processor and tries to steal work from the other processor. So this processor might say, I'm just going to steal work from this guy. This processor might say, I'm going to try to steal work from this guy. But it's going to fail because there's nothing here. This processor might say, I'm going to steal from this guy, but it's going to fail. There's nothing there. Okay, and then they just keep trying like that. But this guy's going to take this and execute. That might then, it's not going to do anything. It's going to be idle again, and so on. Now, the key point here is that the thief, the guy that's stealing, operates on the other end. And the guy that's actually working on the queue operates at the lower end. So they operate at two different ends, and that's important because basically they don't contend. Yeah. So there's no contention between. There could be contention if there's only one thing in the queue, but otherwise there's plenty of space for them to do their thing without getting into each other's space. Okay. Now, this algorithm is a concurrent algorithm, right? It's not a parallel algorithm anymore. Does everybody know what I mean by this?
You're mutating.
This is horrendously mutateful, effectful, whatever we want to call it. Like, there's just shared state up to wazoo, right? This is all shared state. Everybody has, this is like a wild society. If I don't have enough money, I go steal from somebody, right? It's just so it's just incredibly concurrent algorithm, and incredibly challenging to implement efficiently and correctly. I think I wouldn't be exaggerating if I tell you that probably there has been a sequence of at least 4 or 5 papers on this. Like initial concurrent data structures were for this problem were developed in 1995-ish, and they had all sorts of limitations. These pools were fixed size. They were implemented as arrays. They could overfill and so on and so forth. And then it took another 10 years for sort of what you would expect as reasonable algorithms to be developed that allow you to implement this algorithm efficiently on any number of processors. They still have limitations, but they're reasonable. Okay, so incredibly complex. Now, this is an important point, right? So if you don't have abstractions, effectively what you end up doing is implementing this or something similar to this in your own parallel algorithm in order to get the efficiency benefits of algorithm. You basically have to do your own scheduling. Now, if you have an abstraction and if you have a cost model, this is implemented in the runtime system of the programming language for you. You don't even see it. You just write code at the level of lambda calculus. You say, these two are going to run in parallel. I don't want to think about it. And the runtime system figures out how to do the best scheduling. Okay? Now, it turns out this was an important result. An important result in the field was that this algorithm actually gives you W over P plus S with high probability. Not quite high probability. I mean, high probability bound is a little bit more complex in expectation. Obviously, this is a probabilistic algorithm, right? Like, so these steals are happening uniformly. When somebody is idle, a processor is idle, it picks a uniformly random processor and tries to steal from it. So it's a probabilistic algorithm. So in this bound is that the expectation of T sub P is that W over P plus S. So it matches this including the cost of the scheduler. That's very important, quiz point. This bound actually includes the cost of the scheduler, right? Not only is it bounding TP, it is also accounting for the cost of the scheduler, and it's saying all of that will be done in W over P plus S. So this is basically saying the high-level cost model is truthful. We can implement it efficiently, matching that bound with reasonable success. And in fact, there has been many implementations of this, right? We implemented one in our research group. Guy Blalock and his research group implemented many variants of this. Other people have implemented this. This is just widespread. Right? Yeah.
This is still the idea of greedy scheduler.
This is the idea of greedy scheduler, and how do you implement it in a distributed fashion like this? Yeah.
But this looks like work is doing scheduling because we are stealing.
Yeah, absolutely. Oh, I should have mentioned that. Sorry. This is called work stealing. Yeah. It's a pretty bad omission. Yeah, this is called work stealing. Right. It goes back to 1980s. Right. This was proposed in 1980s by Burton and Sleep initially. And the theory behind it was developed and analyzed by Charles Lyserson at MIT, Guy Blalock, and Robert Blumoff, and their teams, their research groups. So these are sort of the main people that developed the provably efficient versions of these. There are many variants of this. Some of you asked about cache locality. People have studied cache locality of this algorithm. They've proven that it has very good locality. And the main reason that it's very good locality is that it mostly simulates a sequential execution, except at these steal points. At these steal points, it deviates from sequential execution. But other than that, it's very much consistent with sequential execution. So beautiful work. But all of this works, right? All of this is available to you in at least several programming languages. It's available in Java fork join. It's available in Parallel ML. It's available in Silk. It's available in Xten. It's available in Java Habanero Java. Am I missing, I think? It's available in Haskell, but its cost is a bit shaky. But I think it is available, yeah. Questions? Okay. If you're curious, I could tell you a little bit about the intuition for why this works, but I think we are out of time, and I don't want to abuse my time here. But if you're interested in knowing more, I can tell you more about why this stealing thing actually works. Yeah. Okay. Thank you for your attention, and we'll see you in the afternoon. Yeah.